Oh, hello. Piyush, are you there?
Hey everyone, am I audible?
Yes, you are.
Okay, great. So we'll wait for a couple of more minutes and then start.
Thank you.
Good afternoon, everyone. A very warm welcome to the session. I have given the presenter rights to our first presenter, so whenever you feel fine, we can start.
Yeah, so let's wait for a couple of more minutes. This is Arun here. So
Sure, sir.
yeah, so one more minute or 2 more minutes and then we start. Let's wait for a couple of more people.
Sure, sir.
All right. So welcome everyone for the inviter paper session on content understanding. Today we have total 4 papers that we're going to listen to and then discuss. Um, so so each paper has 20 minutes. Let's present for 15 minutes and then maybe leave 5 minutes for question and answers. And then if anyone wants to interject and clarify certain things, they can. We can do so. But for detailed questions, please wait till the end so that it is sort of semi-organized. And let's keep a watch on the time. So with that, we can begin with the first paper. Vita, I think you can start.
Thank you so much. I'm going to share my screen. Would you be kind to tell me if you can, are you able to see my screen?
Yes, we can.
Okay, great. Thank you. Hello, everyone. I'm Bita Hushmet, a graduate student from Ryerson University. And today I want to talk about our recent work with Dr. Han, who is a professor at Ryerson University, who is also my supervisor. I want to talk about facial expression recognition under partial occlusion caused by virtual reality headsets. I will give you a brief introduction and background on the problem, and then we'll go over methodology, experiments, and finally, I will talk about conclusion and future works. Facial expressions of emotion are a major channel in our daily communications, and it has been subject of intense research in recent years, especially CNN-based approaches due to their proven ability to facial expression recognition task, or in short, FAIR. Also, FAIR has a lot of applications in different areas, including interactive game design, security, driver fatigue monitoring, and many more. On the other hand, we have virtual reality, which has gained popularity as an immersive multimedia platform where FAIR can provide enriched media experiences. However, recognizing facial expression while wearing a head-mounted VR headset, as you can imagine, is a challenging task because the upper half of the face is completely occluded. In this research, our objective was to automatically infer facial expression in presence of a severe occlusion where the user is wearing a head-mounted display in a VR setting. We proposed a geometric model to simulate occlusion resulting from a Samsung Gear VR headset that can be applied to existing FAIR datasets. And then we also adopt a transfer learning approach starting from 2 pre-trained networks and further fine-tune them on 3 benchmark datasets. I think it's important now to talk about a bit about occlusion. Partial occlusion is a common problem in FAIR and very frequent in real applications. It can introduce errors into the predicted expression and significantly decrease the FAIR performance. This is because basically the presence of occlusion increases the difficulty of extracting discriminated features from those parts that are occluded. And it's not bad to know that there are 3 types of occlusion. Temporary occlusion occurs when part of the face being obscured temporarily by self-occlusion. For example, your hand can become in front of your face, or you can move your head. This is all occlusion. Systematic occlusion can be caused by the existing of 1 or more facial components like hair, mustache, or a scar in the face, or by people using different accessories, which in our case, VR headset is an accessory. And lastly, hybrid occlusion, which arises in the presence of both systematic and temporary occlusion at the same time, which happens a lot in real-world situations. And also, this is happening in our case. In the literature to address occlusion issue in FAIR, some approaches focus on feature reconstruction methods that recover clean faces from the occluded ones, and some approaches rely on automatic feature engineering using deep learning method and also transfer learning. But let me here review the related approaches to ours, which is facial expression recognition under occlusions caused by VR headset. To our knowledge, there are 2 studies that focused on the same problem as the problem that we're working on. In a recent study, 2 models, namely VGGF and VGG-face, has been trained on modified training images in which the upper half of the face is completely occluded. The authors first trained the network on images with full faces and further fine-tuned the models and images in which the upper half of the face is occluded. The other study was conducted by Hickson and his colleagues, who proposed an algorithm to infer expressions by analyzing only the images of a person's eye captured from an eye tracking enabled VR head-mounted display through internal gaze tracking camera. However, we think that as not all VR headsets include eye tracking sensors, it is better to consider an approach utilizing external camera in VR system, which is more generalizable and cost-effective, like the first study. And we also took the same approach, but a key limitation in the first study is that they simply covered the upper half of the face without taking into consideration realistic occlusion arising from VR headsets, which we attempt to address in this work. I'm sorry. How we tackle fur under occlusion? First, as there are no standard dataset containing occluded face images, we established VR occluded images by masking on the standard facial expression images that already exist. The process consists of three main steps: face detection, landmark detection, and also applying VR patch. To simulate the occlusion, face detection is applied on grayscale images based on the modification to the standard histogram of oriented gradient and linear SVM-based method for object detection. In order to estimate the 68 points, which indicates the facial landmarks that map to facial structure, we followed the FaceNet approach trained on the IBOC 300 face landmark datasets. And for applying a VR patch, we initialize VR dimensions based on the Samsung Gear VR headset. And as you can imagine, typically a resized set of training images have faces filling various percentage of the image, and it is unlikely that a fixed size covering mask fill fits all the training images. To account for that, and for uniformly scale the VR patch and the training images, we used the distance between two temporal bones of the facial landmark as a reference layer. Then we generated the polygonal occluding patch by setting the midpoint of the line passing through the eye centers as the center coordinate of the VR headset. And to account for the rotations, as we can see, head can easily rotate. And for account for that, we aligned the resize patch with the axis running through eye centers to reflect accurate simulation of a VR headset in various situations. If I want to elaborate more on that, we obtained the angle of incline by determining the inverse tangent function of changes in y coordinates to changes in x coordinate of eye center points. And then we utilize the rotation matrix to rotate corner points of the blocking patch about its central pivot point and the coordinate plane accordingly. This geometric model provides a more realistic occlusion resulting from wearing a VR headset rather than simply covering the upper half of the face as done in previous works. As we know, in CNNs, images from different data sets share similar low-level features after the convolutional process. As it is costly to train a network from scratch, especially on small-scale data sets, an alternative training strategy for new data set is utilizing parameters transferred from pre-trained models and fine-tuning them on the basis of the new data set. Thus, for classifying facial expression under severe occlusion, we choose two popular architectures, VGG and ResNet50, pre-trained and a face recognition task, which is closely related to ours. We proceed our work by fine-tuning the models and occluded images generated through applying our geometric simulation model, as we discussed earlier. As you can see in the figure, the custom VGG face, because we modified the VGG face, obviously has 13 convolutional layers and 4 max pooling layers, interleaved with dropout layers, as dropout layers are effective in avoiding the model to overfit. If I want to get into more details, starting from second block, after each convolutional layer, a dropout layer is added with rate starting from 0.5 to 0.55. After all the convolutional layers, 2 dense layers are added, each with 512 hidden nodes, followed by a 50% dropout layer. And the final dense layer is followed with a softmax layer consisting of 8 nodes for 2 of the data sets and 7 nodes for the other one to generate the output. And in the case of ResNet50 architecture, layers pre-trained on VGG face dataset are transferred to our deep CNN model, followed by 2 dense layers with, again, 512 hidden nodes, and replacing the last 1,000 fully connected softmax layer by an 8 fully connected softmax layer in case of 2 of the dataset and 7 fully connected in case of the other one. We also adopt batch normalization right after each convolution in the case of ResNet architecture and before activation. To evaluate our model, we used three popular facial expression datasets, FurPlus, RAFDB, and AffectNet. RAFDB is dead and AffectNet is the middle one. Both FurPlus and AffectNet have 8 basic emotional classes, including anger, disgust, fear, happiness, neutral, sadness, surprise, and contempt. And RAFDB has 7 classes. It doesn't contain the contempt class. And in the slide, you can see the sample images of each database and also distribution of data in each of their classes. The input to our CNN is set to a fixed size, a 224 by 224 pixel image. We rescale all training and test images before training to this size. All images are normalized by min-max normalization, and the models are trained using data augmentation, which is based on including horizontally flipped images. The training is carried out by optimizing the multimodal logistic regression objective using mini-batch gradient descent based on backpropagation with momentum. You can see the batch size, momentum, and other hyperparameter details in the slide. The training was regularized by rate decay, specifically the L2 regularization. We've utilized adaptive learning rate, initially set to 10 to the power of -2, and then decreased by factor of 10 when the validation set accuracy stopped improving. In case of modified ResNet 50 architecture, we also regularized training by setting maximum norm kernel constraint. We've also adopted early stopping approach. During training, the model is evaluated in a holdout validation set after each epoch. If the performance of the model and the validation set start to degrade, including loss begins to increase for 10 consecutive epochs, then the training process is stopped. And for sure, we monitor loss at the end of every epoch. For each model, we trained our networks and each dataset separately with 5-fold cross-validation and report the average accuracy numbers. It can be seen from the table that training models from scratch, because we also trained models from scratch alongside with the transfer learning. So we can see that models from scratch provides less accurate results in comparison with transfer learning-based approaches. The VGG-based architecture, pre-trained on VGG-based dataset and fine-tuned on FurPlus dataset, achieved accuracy of 79.98%, which is the highest among the tested model in the study. Comparing the result with the results reported in a related work in the literature, we see that we provide a slightly better accuracy on AffectNet and a slightly worse than FurPlus. However, it is important to note that our geometric occlusion simulation model result in more realistic occlusion, while in the previous work, the occlusion was generated by simply covering the upper half of the face. Although these results are not directly comparable, but it shows that simulated occlusion with transfer learning can provide promising results by utilizing existing benchmark datasets. And for analyzing the results further in detail, we can take a look at reported F1 score, confusion matrix, and precision or recall plot for each class. We see that some models from F1 score table and also from the precision recall and also confusion matrix as well, that some models are performed better in classifying a specific class, and models from scratch couldn't classify instances from anger, contempt, and disgust classes. We also can see that, for example, ResNet 50 trained on FurPlus doing well in classifying happiness class. We can also see that in those, from the confusion matrix, in those instances that are misclassified, in most cases, the contempt expression misclassified as neutral, which might be because of the nature of the expression in which the lower half of the face is somewhat similar to when we express neutral expression. And in conclusion, we modified 3 existing benchmark datasets to mimic VR occlusion by utilizing our proposed geometric simulation model, and also proposed a transfer learning method for addressing the facial expression recognition in presence of severe occlusion where the user is wearing head-mounted display in a VR setting. We test 2 popular architectures, as we discussed, VGG and ResNet 50, pre-trained on VGG face database, and further fine-tune their parameters and occluded images for plus AffectNet and RAFDB. Our work showed that the information required for successfully classifying various facial expression exists in lower part of the face, and our method achieves performance comparable to the state-of-the-art result. And for future work, we are going to study how to integrate approaches using external cameras and method utilizing internal cameras like ours in VR system to improve the accuracy further and provide a rich engagement experience for virtual reality users. And this concludes my presentation, and I'm open to any questions you might have.
Thanks, Peter. Does any of you have any questions? Attendees, if you have questions, you can inform us, or you can also type it in the chat box. We'll convey it to the presenter. So, any of you have any questions? Questions for Beta? All right, let's thank Beta for her presentation.
Thank you so much.
Yeah, so thank you.
Thank you.
The next paper will be presented by Vishal. Vishal, are you there?
Yes, yeah.
Yes, so you can begin your presentation.
So I believe the screen is visible, right?
Yes, it is.
Okay, all right. So, hi everyone, I'm Vishal Udandra, and I'll be presenting the paper on the inference of soft biometrics from typing patterns collected in a multi-device environment. So this is joint work with Mohit Agarwal, Rajesh Kumar, and Rajiv Ratan Shah. So I'll begin with explicating the problem definition and what literature in this line of work has entailed. So we all interact with a lot of computing devices these days, and we leave a variety of footprints, such as typing, swiping, walking, among others. These footprints have been studied in recent literature for authentication, identification, and forensic analysis, and they've been used to retrieve soft biometric attributes. For example, a soft biometric attribute could be like the age of a person, the weight of a person, the height of a person, and such. So, in our study, the hypothesis is that typing is an indispensable part of our lives, and thus we believe that it reveals a great deal of information about the soft biometric attributes. So, we basically conduct an empirical exhaustive study from typing patterns to retrieve age, gender, and such soft biometrics. And we want to sort of give an overview of where the field is currently and what all can be done in the future. So I'll just list down a few motivating use cases. The first one is personalized user experience. So consumers often refrain from providing too much information while signing up for information technology enabled services online. But organizations can use uh, soft biometric attributes gauged from consumer typing patterns to tailor their platforms and services as per the user's demography. This would help provide a much better and seamless user experience. Second one is improved recognition rate. Um, Using these soft biometric attribute retrieval or algorithms can help improve the recognition rate of authentication and identification systems. The third one is targeted advertising. Organizations can use soft biometrics for customizing their advertisements and targeting people of specific soft attributes. This can again lead to more uh, accurate retrieval systems. The fourth and fifth one are quite related. Both of them deal with the fact that forensics is a very important role in the current ecosystem. So, according to an FBI report on internet crimes last year, around 467,000 online scams were registered in 2019 alone. So, this sort of gives us a motivating use case to build a system that should be able to uh, tackle such online scams from happening. And we believe that using soft biometric classification and regression algorithms can be used to prevent such online scams. So, continuing from the previous example, this is an example scenario that can help further motivate the work. So, the person in the middle is somebody called Benjamin, and the person on the left impersonated Benjamin's typing habits to basically scam the person on the right, whose name is Rosalie, by promising her lifelong love, and she basically lost $90,000. So this is sort of like a motivating example that can uh, tell us why this problem is very prevalent in the current scenario. We do, of course, acknowledge that this is not a foolproof scenario, but this gives us a guiding principle to follow this work. So in this paper, we make a five-fold contribution. The first one is we investigate the inference of five different soft biometrics from collected from different devices. We benchmark 6 ML and 4 DL algorithms for the classification of these said soft biometric attributes. And we also provide uh, a holistic overview of the different feature sets that can be used from typing features. We again share the code base for reproducibility so that this can engage future researchers in this direction. So the dataset that we use is the Syracuse University and Assured Information Security Behavioral Biometrics multi-device and multi-activity data. This dataset collects typing, gait, and swiping data from 117 users engaged in a series of tasks. For this work, we limit our scope to the typing based data. So the typing data has been collected in two different forms. One is called fixed text. Fixed text is basically where users are asked to type in a fixed sentence according to their typing style. So the data is consistent across all users since a fixed sentence is given to type. The second type is free text, where users are given a series of questions of different cognitive load and they are free to answer according to their health. So this data is not consistent across users, but it still gives an additional dimensionality to the research study. And the data was collected on three different devices: desktop, tablet, and smartphone. And we provide a study on all three devices. So yeah, how do we extract features? So the data that we have is in the form of keystrokes along with their press and release timings. So I'll explain this with an example. Let's take the word of Leo. So there's a key press time and a key release time for each of the characters. The first feature that we extract is something called unigraphs, where we consider every character and the feature is basically the difference between the key release time and the keep rest time. Now for the digraphs are basically with respect to two subsequent characters in the sentence. So in this word, it would contain LE and EO, and there are four different types of digraph features corresponding to the different release and press timings that we obtain from the characters. And finally, we propose a new sort of a feature extraction procedure, which is with respect to the level features, unigraph and digraph features across the word using an aggregation function, and this sort of gives us a global feature set as compared with the local unigraph and digraph features. So now that we've covered the feature extraction procedure, we basically use a learning framework that consists of using 70% for training data, 70% of the users. So that is approximately 82 user data for training, and about 35 for testing. And this is a standard learning protocol that is used in most in machine learning work. Now we come to the models that we use. For machine learning, we make use of these 6 models, and the major motivation is based on previous studies as well as using different models from different learning paradigms. And coming to the deep learning method, we use 4 of them. The first one is a fully connected network. We use 4-layered neural networks with ReLU activations. And the motivation here is that it should help capture the intrinsic differentiating factors within the aggregated feature vectors. We make use of CNNs with 7 layers, 4 2D convolution layers, and 3 FE layers. The motivation behind using CNNs is that the features extracted using the feature extraction protocol can be highly correlated. So when we convert those into an image sort of a data, we can easily exploit the spatial and structural correlations present within the data. And since we already know that there are correlations present in the data, this should help provide a better feature map representation. We make use of 2 temporal-based models, recurrent networks and LSTM networks. Again, the motivation here is that since the data is correlated, we can make use of these correlations not only in the global setting, but by spreading them across time and treating it as a temporal correlation data. So we now show the results that we have. So the 5 major soft attributes that we are predicting are gender, major, minor. Major, minor is essentially the uh, uh, major of the person that is being recorded. So, for example, the major could be computer science or electronics and communication, mechanical, stuff like that. So, for gender, we see that our results are pretty good in the sense that we are able to get around 86 to 90% accuracies. And so, this shows us that we are able to predict gender well from the given feature sets. Now for major minor, similarly, we achieve a highest accuracy of about 87.8%, and this should again give us an idea of where the field is currently at and how it can be used to predict major minor. The next one is the typing style. So typing style is basically what kind of a typist is the person. Like, is he a left-hand typist? Is he a right-hand typist? Or stuff like that. So again, here we achieve very good results. And the next two are age and height. So for age and height, we treat it as a regression problem rather than a regression problem. And we again get mean absolute errors of around 1.7 to 2, which is a pretty good result for predicting age and height. So now that we've shown the results for our work, we do a qualitative comparison with the recent literature that has been shown in this particular area. So as you can see from the table, we see that recent literature has either focused only on free or fixed text, but do not consider both methods. Similarly, they only restrict themselves to a certain class of problems and not to a holistic problem setting. And they again restrict themselves to only desktop or phone. We, however, consider all three devices: desktop, phone, and tablet. And so this table should give us an estimation of where the field is currently at, whether we're able to do well in predicting soft biometric attributes, and what are the future goals that should be achieved from here on. A few limitations of our work. The first one is the requirement of a quality data set. The data set that we use currently is limited because the number of subjects is quite less. 117 is not a lot of data. The next thing is dataset imbalance. So currently we have some imbalance in the dataset, and we tackle that using oversampling for the minority class, basically using SMOT and borderline SMOT and ADASIN. But again, that is more of a synthetic solution rather than actually building a better dataset. We do expect that the performance of these proposed approaches would scale to a larger dataset, but it is of course difficult to claim that it would without actually testing it in with rigor. Finally, we show that we explain that there are a few ethical concerns. Of course, the work that has been done here can be used with for malicious purposes by people, but this should be prevented by developing existing as well as new public policies, which is of course out of the scope of this work. Finally, we conclude that basically soft biometrics such as gender, typing style, major, minor, age, and height can be inferred from typing patterns. And we show that these inferences can be done with uh, substantially good accuracy. And we, of course, motivate future work by showing that this problem is not yet fully solved and it can be extended. A few extensions that we would like to do in the future. First one is we want to test these proposed approaches on multiple datasets in the future with more diverse backgrounds and demographics. We want to conduct an ablation study of how accurate the system is for different groups within a particular class. And we would also like to investigate other modalities available in the given dataset. So the dataset contains, apart from typing style, it also contains swiping and gate data, and it's an interesting open problem to see how these three modalities can be combined to better gauge soft biometric attributes. For more details, you can check out our paper, and we have made all of our code open source so that it fosters research in the future in this direction. So that is it from my side. If there are any questions, I'd be happy to take.
Thanks, Vishal. So, do we have any questions to Vishal? Please do ask your questions. Any questions to Vishal? All right. Thanks, Vishal, for presenting your work.
Okay, thank you.
Yep. So, Shriyashi, can you hear us?
Yes, I can hear you. Hello.
Okay. Yeah, you can start your presentation.
Okay. Thank you, everybody. Okay. So, is my screen audible, visible
Yeah, it's
to all?
visible. Yes.
Okay. Okay. So, our topic in this work that we presented in Week was semantic enhanced sketch-based image retrieval with incomplete multi query, where By query, what I mean is to start with, at least we will be given with a hand-drawn sketch, which might or might not be accompanied by text. Whether if it is, then it's called multimodal. Otherwise, it's just a unimodal, which is sketch. Now, because one of the fundamental challenges of this kind of problem scenarios is that the cross-domain gap. How do you at all connect these sketches with natural images? And more importantly, when we try to connect them together, the point is who is going to draw this exact same sketch for you. One of the ways of compensating to that kind of lack of functional one-one correspondence is to use the age map. Now, you just use the image and convert it to the age map. That's going to even cause a bigger trouble in terms of introducing a lot of noise. A sketch is not essentially the age of an image, right? We can draw much better, much meaningful some age sketch than an age map can at all pass with. Then a step forward is introduce a kind of little more information whether what are exactly looking for. Sketch is one, and text description. Now, text description, when it comes, when typically what we end up using is that, well, I'm looking for, if it is for a recommendation system, then you see that, well, I'm looking for shoe, or I'm looking for single word label kit information, which again, yes, does help a step forward, but doesn't really always reveal all sufficient characteristics on the object specific fine-grained attributes. So with those challenges, sketch-based image retrieval continues to improve, but the primary contribution of our work was kind of connecting three of them together, where sketch as well as a text-based attribute information. Now, text-based attribute information is much bigger than a user is allowed to provide a little more information than just single level sketch query. And here, when we saw that when we need to connect the sketch and image together to estimate the functional correspondence between these two modes, there our contribution was how do we introduce more fine-grained information. Now, information can happen in fact can be shared at various levels of details, right? So the contribution of semantic enhanced joint embedding was transforming the initial generic sketch into a more comprehensive joint descriptor by introducing details at various levels. Then that's why we call it a hierarchical level of details that information can be passed when the joint embedding space is being learned. So that's what kind of overview of our problem. So I just want to walk you through the actual diagram and actual the process, the sequence of action. So essentially, user is going to give you either as a query or image. Now, whatever it is, this can be converted into sketch-like. Yep.
So someone just raised their hand. Surabhi, do you want to say something?
Sure.
Surabhi, do you have a question? All right, I'm not sure. Yes, Surabhi, can you hear us? Do you have a question? All right, let's proceed. Let's proceed seriously.
Okay, sure. So that's kind of usual sketch. Given a rough sketch, how can you introduce the domain-specific context? That's kind of fine-tuning, which we'll call it. Now, we also have two parallel regularizer network where each of these networks are essentially initialized with unimode information. For example, if you have a bunch of images, we have a bunch of images, so we can, initialize image regularizer network by the unimode information where by a collection of image represents one specific category. Similarly, you can do the same for the text attributes. Now, the way we want to fine tune the sketch feature, not necessarily just plug this derived feature, what you can see at the end. It is not necessary to have this kind of whether it is non-linear embedding or any linear embedding, whatever it is. Just connecting them together when the things are already learned is not necessarily the best possible way of doing it, because that way we are kind of, as we can see, that at various layers of details, various information could be shared, but which we are missing. We are just relying on one specific layer. So that's where what we did is let's share the information at every level. That's one. And while doing it, we can actually concurrently fine tune the three modules together. So now, when we talk about learning them together, there are a few loss functions that we are working on. One is embedding triplet loss, because as you could see, the triplet loss was important for our scenario, because as you could see, there is a kind of unbalancedness in terms of mode specific representation. For example, if I ask for kind of images representing a specific object category, there are plenty of it. You can just grab it from anywhere. That's easier. But when we want to represent the same object category using sketch or little more descriptive information, things turn a bit difficult, right? So with that, we need to take into consideration of how to introduce more discriminability within the learn descriptor, where things, they do the joint feature embedding at the joint feature embedding space. The learn descriptor ends up learning the exact unique characteristics of each of these object categories only at the category level, not necessarily at a very instance level. Now, the third component is the classifier loss. With all of these components together, we have the joint embedding loss, and this is the entire, we call it method in motion, which essentially runs hand in hand to concurrently fine-tune the entire learning module together, which was initially learned based on a unimode, now updated, I would say, in a joint learning framework. So in the whole process, we have joint embedding loss, which has a few components, along with the classifier loss and the triplet loss. And this triplet loss, we do it in a bimode manner, where in one module, we want to find out the discriminable characteristics of that specific sketch while combining with this text, and in a parallel module we do it for how the sketch represents the unique characteristics of the specific object instance along with the image. So these two happen independently, however, in a very concurrent manner. So these are the loss components which are joined together to introduce a joint embedding loss. And finally, we are essentially talking about retrieval. So in order for us to define the discriminability score of a query sketch, given a sketch, how do you at all find out the dissimilarity with its with a given image in the database. So that's why we have um, uh, the dissimilarity score, which takes into consideration of both the joint embedding differences, Euclidean difference between the joint embeddings, and as well as the triplet losses. Now here we are considering, because we are just matching with the um, image, so we are just using the triplet loss, which is accountable for identifying the discriminability along with the image. The other advantage of using this dissimilarity score is that we are not essentially looking for the sketch versus the entire image, because when we talk about object rather anything specific about this image, there is an attention region. So in place of using the whole image, we end up decomposing it a bunch of proposals, and the sketch is kind of matched with this proposal, and the joint embedding feature learned using this using our module is used to find out the differences in the joint embedding space for each of these proposals along with the sketch in hand. So the other component of our this query can be a text description. So in case we do have then access to extra text specific information, we can as well add that to compute the dissimilarity score along with its corresponding triplet loss components. So we have used this this work to demonstrate the performance on these publicly available datasets, extended sketchy as well as tubalin. So both are kind of big data, kind of large data sets. Extended sketchy has about 125 categories. Tubalin is even further larger, where it has about 250 categories. So as we could see, we compared to state-of-the-art results, we have been able to achieve around 2 to 6%, in fact 6 or 7%, whatever it is, 3 to so that's kind of improvement that we could observe just by using the sketch-based retrieval component, and things can done further rosy when you end up using the descriptor, text description, right? So with text description, we can achieve further to around 2% more improved MAP score. So these are some of the example results for our work. As you could see here, we do have some kind of false positives, where this was an image from a shark category, if I'm not wrong. So that was one of the, but that essentially look very similar, and we end up getting trapped with the false positives. So these are some results of our work. And this is from tubalin, which has about 250 object categories. So end of the day, we realize that description is definitely more useful than just passing a single word level information. And in place of just relying on learning a joint embedding descriptor at a single layer, it makes more sense, or it is helpful to combine the information in a multi-layer framework, which can help introduce a more descriptive as well as representative as well as discriminative at the joint embedding vector. And that has helped us achieving an improved generalization characteristics within the learned descriptor, which we call it SAGE. Any question?
Can I ask a question? I'm audible?
Sure.
Okay.
Yes, please.
Can I ask a
Proceed.
quick question?
Sure.
So I was wondering, how do you balance, since you're taking two inputs for your system, like the text and the sketch? So how do you balance the information, as in if the text is, let's suppose, way too descriptive, like the description, it's not even in the sketch, right? Or if it is adversarial in nature, the text is not in line with what the sketch shows. So how do you balance that?
Well, yes, that's a very good question. So we haven't really considered this adversarial characteristics. Of the. I mean, that may be a challenge if the text is going completely beyond. If it is intentionally misplaced to misguide the search, then it's trouble. And but if you are just talking about the person kind of talking too much. So in that case, what we end up doing is that we just truncate the description by using a set of keywords, by choosing a set of keywords, right? But yes, we haven't really taken into consideration of how does it work in presence of an adversarial letter. That will be definitely a very good extension of the work.
Okay, thank you.
Thanks.
Any other questions for Shriyasi? All right, Shriyasi. Thanks for presenting your work here.
Thank you. Thank you, everybody.
Yes. Udit, are you ready?
Yeah, sure, I can.
Yes. You
Can
can
share
start.
my screen. Okay, is my screen visible? Okay. Okay, I hope it's visible. I'm not used to the WebEx interface. Okay. Can somebody cue me whether it's fine or not? I can just begin there.
So
Yeah.
you are looking at your screen. I mean, we are looking at your screen.
Oh, you're okay. So how do I change this? Wait, is this good now?
Yeah, that's better.
Okay. Okay, sorry for that. Okay, hey everybody. Today I'm presenting this joint work with Dr. Arun Balaji. This is a fine-grained language identification with multilingual capsule networks model, in short for CapsNet. Okay. So the problem task is pretty simple, but not so simple to do it. But the task is simple, to identify languages. Okay. So the need is, I think it's pretty clear for everybody that you can use it for emergency call routing services, voice assistants, conversational AI, and of course, speech is the easiest form of communication for humans. So it makes sense that AI would jump into this land and communicate with us in our language, be able to detect our language. So, what are the trends in language identification these days? So, iVector has been something which has been a really popular go-to way for language identification since a very long time, I think 10 years or so. So the idea is that you embed everything into a fixed size space and then work on it. Something similar as DNNs do. The other works might involve, you can have hand coded features like phoneme detection, or you can have spectrograms. So in this work, we will focus on how to use the image domain, leverage it, and get the results on multiple languages, like be able to detect multiple languages. So that was the data set part, like the kind of data that we're using. But people have also used SVMs, HMMs, GMMs, regression. More recently, they've used bidirectional LSTMs or RNNs and CNNs to do classification. But there are a lot of issues with using those techniques. So I think one of the major issues is that manual feature extraction is very hard. So you don't need to do that. And there are works which have started in language identification, which shows that neural networks are enough to extract, but even they lack something, which is the second point, as in they require a lot of data. So everybody knows that neural networks require a lot of data, and they can be prone to noise. So when noise is injected, they're bad. And even more so in application-based scenarios where you don't have injected noise, but rather you have some actual noise, then even then they don't really perform well. So we'll look into how to solve that. So the problem characteristics are such: we'll be given some short snippets like 5 or 10 seconds. We have to detect multiple languages. They might contain noise. We have to do so, or at least try, using very less training data. And well, we'll hope that the data collection is easy too. What we'll do in this work is have a non-class verification step. It's another name for out of distribution, detecting out of distribution samples. So we want to detect if a language is not part of the repertoire of our 10 or 5 or how many languages we trained our model on. And we hope that everything is multilingual. I'll go on with the definition of multilingual when we get to that slide. So would be using total of 10 languages, but it's essentially 5 languages for the LID task, that is the language identification task. That's the red ones, the first 5. And we would be using the remaining 5, which are the blue ones, for the non-class detection, as in given, say, Turkish, that's the first in these 5. We should be able to say that, well, Turkish is something that is not in the first 5 classes. We wouldn't know it's Turkish, but we'd still be able to say it's not among the first 5 classes. So why is it important to reduce the data requirements? Is because what we want, like the hope, is to one day use regional languages as like be able to create models for regional languages. And it's very hard to collect data for those languages. It's not widely available, it's not there. Plus there can be a lot of noise into it. So let's talk about data collection here. So what we do is we collect our own data for this work. We use YouTube as our source, and we curate it through saving audio recordings from local and global news, interviews, speeches, etc. And the data size is 100 hours per language for the LIG task. That is the first 5 languages that we said. And for the remaining 5, that is for the non-class analysis languages, we have a total of 5 languages, and per language we save 30 hours, 20 for training and 10 for testing. And it's a similar 2:1 split for LID task, 70 hours for training, 30 for testing. So you see, since we're using YouTube as a media to collect data, it becomes pretty easy to collect. But of course, it comes with a cost, and that is it has a lot of noise. And that's something we want to solve as well. So instead of going for the injected noise way of like doing the work, we went for a way that so that it could be used in real life scenarios where there are no injected noise, but rather there are, well, these 3 kinds of noise that we could list down. First is, well, you could hear. So there are 2 parts to it. First is whether you heard some language or not, which are the first 2 things. So if you know that you heard something and it was a spoken language, but you might not know which language. Second case could be, well, you know which language as well. And third case could be it's just random background noise which is there. So these 3 types of noise were available in throughout our data. So yeah, we believe that our model is robust to all of these. So the processing is pretty simple, since, as I said, we are working on the image domain of these acoustic datasets. Therefore, all we needed to do was to convert the audio format, like the audio, from audio format to spectrogram images. So the work involves these parts. First is to handle the problem in image domain. So there are a few complications I'll make sure you guys know, and which is why that motivated us to use something known as capsule networks. We will compare this work with the current SOTA or the state of the art that includes CNN with bidirectional RNNs, and one of them as a baseline we consider with attention. Finally, the best model that we could create with CapsNet involved a deeper variant of it. We'll have a look at that. And finally, we'll verify, we'll present the non-class detection scheme that we have. So how does sound look? So in the images that you see on your screen, the left and right one are really, really different. In fact, they are the two extremes of music notes. But for a CNN, they might look very similar. When we look at those images in a spectrogram format, things are even worse, because what you see on right is basically a vertical line in the spectrogram. So the color in the spectrogram is basically the intensity on right side. So if this image is given to a CNN, it will consider most of these pixels as noise and just disregard them. And there is a reason why. So I'll get to the reason. First, I have to make sure you guys know that we're using spectrograms. And there is something else known as mel frequency septrons. We don't use it for now. If anybody has any questions why, we can just take it up later. So let's get on to why do we use CapsNet theory? Why do we use CapsNets, and get on with CapsNet theory and see why using this is better than CNNs, and why do we have to use this? Like, CNNs is not the answer. So CNNs are good, but they have a problem, which is they are positional invariant. So if there's something like this, like a boat here, all the boats in this slide are exactly same for the CNN. So the problem I'm trying to hint at is CNN views objects and the orientation is part of that object. So a boat being upside down is a part of being a boat, right? So it doesn't know that the boat is upside down. So this is, I think, known as a Picasso problem. So here in the spectrogram, if we try to map this problem, so if sounds were supposed to lie on any other vertical line, maybe, can you guys see my pointer, like my cursor? Anyway, if you take any two lines, okay, anyways, I can continue. So if you take any two vertical lines, they might as well be the same sound, but in different location. So it becomes really essential for us to preserve the orientation of that pixel, right? But what CNN would do if we were to give this is, okay, I might not have that right. Okay, what CNN would do here is use something known as maxpool, which I think people are aware of. It would just remove all those points and take the mean or max of it, and all that information is gone, right? So most likely you omitted a large part of sounds which were there in that region. So that's not the right way to do it. So the problem that I just mentioned is known as positional invariance. What we really need is known as equivariance. That is, if my orientation changes, that is, if a sound from the left part of the spectrogram goes to all the way to the right, the CapsNet should know that it has gone there. So what we need are two things. First is the detection of something like some object, which is sound in this case. And second is the orientation. Where is it? That's also important. So how CapsNet does it is by using something known as routing by agreement. And as an additional benefit, CapsNet are known to have really good data efficiency. So they require really less data. So in fact, as I said, we use around 100 hours of data per language. Other works that are there uses, I think, 4 or 5 times of that. Okay, so I think we can skip the theory for now. If people have questions, we can go over this. So this is the architecture that we are using. It's a simple architecture. We given the input, given the input spectrogram and extract some features using the conv layer at first, and then we begin to use the capsules. Okay, so I'm not sure if my pointer is not right. Okay, so the third block from the left is the primary capsules. So that's basically the capsule network. And our addition to this architecture was presented first by Frost and Hinton way back, I think 2-3 years back. So we added a mid-caps layer. It might seem a small addition, but it did wonders, at least for the results that we have. Okay. So in general, what people think, so this is an encoder-decoder architecture, right? So until the lang caps, which is the classification layer, it is the encoder architecture, and beyond it, it's the decoder, right? So what people usually think of as a encoder-decoder is the classification layer would be the bottleneck, as in the smallest layer in the encoder-decoder thing. However, in our work, mid-caps layer is the actual bottleneck. And I think in our results, we found that having a smaller layer penultimate to the final whatever layer that you require, for example, mid caps to lang caps, or in fact, just before the reconstructed spectrogram, the penultimate layer to it, if it is just shorter than the final layer, things work much better. So this is the capsule network loss. There are two parts to this loss. So the first is the capsule network loss, and second is the reconstruction loss. The one shown here is just the capsule network loss. It basically says, hey, if you are going to classify me correctly, then you have to do it with greater than 0.9 probability. And if you're going to classify me incorrectly, then you should do it with less than 0.1 probability. It's what this equation is saying. So finally, we use a set of CNN-based works, prior works by Bart et al. That uses CNN with RNN. We also added an attention layer to see how things goes. So when I say RNN, I mean LSTM and a GRU. So it makes up two works like that. So the architecture is pretty simple, and it's their architecture. We just added an attention as a third baseline. The non-class detection is pretty trivial in this case because it's a verification step. All we wanted to do is to verify whether CapsNet would be more robust than our baselines. So what we do is a thresholding mechanism, as in we take out some non-class languages and we use a trained model and get the solutions for those non-class languages. And then we figure out that this threshold value works the best and use that threshold value to say, okay, if giving Turkish into a system gives out 0.6, so anything below 0.61, we would consider it as a non-class, that it doesn't belong to any of the languages that I trained. So the results, okay. First, we'll talk about the train and test accuracy. So the baselines, again, I mentioned, there are three baselines that are there with respect to CNNs. And then there are two variants of CapsNet. One, as I said, is the original architecture presented by Hinton. And the second is the one that we have, which includes the mid-caps layer. Now, you can see the CNNs perform really bad. The training accuracy is pretty good. And in fact, it's the best for the BiGRU plus attention. However, if you see, since one of the requirements and problem characteristics for us was to use very little data, this does not hold well for these architectures because they require a lot of data, right? So the test and train accuracy has such a huge difference between them, as against to when you look at CapsNet, the vanilla variant, even though it has lesser accuracy, it's still, you won't say it has overfitted. Whereas CapsNet with mid-caps layer, it has performed very well, at least for the languages that we have tested on. Now, we'll talk about the time to convergence. The BiGRU one took the least time, and therefore we consider it for using with attention. And looking at this, you might think that CapsNet takes 110 hours, which is like 5 times, but that's not the case, because for CapsNet to go beyond any of the accuracies mentioned above, it took, I think, around 20 hours to do that. However, for other languages, so the convergence happened at 110. However, it crossed all those values way back. Okay, we'll look at the ROC curves. For this curve is for the CapsNet. The left one is for test data and right is for training. So ideally, ROC should look like a perpendicular L, inverted perpendicular L, but it's pretty close for CapsNet. However, if you look, so this curve is for BiGRU with attention. If you look, it's really, really bad. Why? Because overfitting is pretty apparent and confirmed with this result. Because the right is more or less like a perpendicular L, whereas the test data, it is terrible. But there is a pattern to this image. So if you look at the CapsNet and the GRU on the right, those data plots, you see that Hindi is always greater than Arabic, always greater than Bengali, more or less close to Chinese, and always greater than English. So this is something that at least we were not expecting. Why? Because Hindi, Arabic, and Bengali are pretty similar. And the fact that these models are able to do very well on seemingly similar languages rather than doing well on very, very different languages is odd. So if we move on to the non-class detection, this point that I just mentioned is again proof. So if you look at the non-class detection, the general trend is that CapsNet is better than GRU, but they're more or less similar. But if you look at the trends, you see the languages we chose are for this purpose. Punjabi is closer to Hindi, but it performs really well. But it shouldn't have because it's closer to Hindi. What should have worked is Japanese because it's different to all the languages. Although Japanese script is similar to Chinese, but the languages are very, very different. However, Japanese is the worst with non-class detection. The same is the case with Turkish and Arabic, which are very close in terms of spoken languages, but the non-class detection for Turkish is pretty good. Spanish and Portuguese are similar with each other and not similar to any other languages, and their final results are pretty similar. So one of the other things that we tested out is to test whether the CapsNet model is multilingual. By multilingual, I mean that if we are given a long snippet, it's not even a snippet, a long audio sequence of 250 seconds, then are we able to detect the intervals where one language was spoken, if there are multiple languages in the whole audio sequence. So what we did is we took out really long sequences, I think about 250 seconds, and then we chunked them out for 5 seconds each, and then we did this test. So in one test, only two languages were there, English and Bengali, and the other English and Hindi. We see that the confusion matrix here corresponds well with the test results that we showed before. So the accuracy here is similar to as before. So we think that capsule networks might be the way to go for multilingual language identification. The future works are, I think, pretty clear at this point because getting the finer classes to work better than the ones which are actually different is something odd and is something we should think about. The second is we can always try out and play around with different architectures. We can have a neural architecture search over these CapsNet architectures, or we can use RNN layers with CapsNet and transformers with capsules. In fact, use of transformers as capsules is something that has not been done, so it's worth a try. We can, of course, extend our work to regional languages. In fact, a couple of days back, IIT Madras had released a huge data set that involved a lot of regional languages. So it makes sense that we go on and try with those. Finally, we can improve our non-class detection. In fact, right now what we have is very trivial, and we can extend non-class detection towards non-class analysis. And yeah, thank you. If there are any questions, I'd be willing to take them now.
Thanks, Mudit. Any questions for Mudit? Any specific questions that you would want to ask Mudit? Please do so. All right, thanks Mudit for presenting your work.
Thank you.
And thanks all for joining today for the invited paper session on
Hello.
understanding. Yes.
Oh, there is a question.
Yes. Yes.
The question is by Adriti Barhiri. So
Yeah.
the question is, what is the intuition for mid-caps layer?
If I understand it correctly, it's, I think, why did we choose CapsNet, or why did we choose CapsNet over any other thing?
It talks about mid-cap layer.
Which layer? I cut off.
Mid caps.
Mid-cap layer. Okay. So you see, in general, we try to add layers to improve the complexity of the model, right? So that was the first motivation to add that. But once we have added, once we did add it and tried out several variations of mid-caps, we saw that creating mid-caps as a bottleneck just before the final classification layer, it really helped a lot. So midcap serves two purposes. First, it becomes a bottleneck, so only the relevant information is there, right? Second, and more importantly, it serves as a good regularizer, right? So I mean, since the spectrogram image, I think if you saw it, you might think that a lot of pixels are just noise, and you would want, like, the network would want to discard it. But if midcaps, like what midcaps allows us to do is to control how many pixels we are discarding, right? There is a trade-off. If you're discarding that, then you might lose on to accuracy, and midcaps tries to control that factor. Just like any other autoencoder thing or encoder decoder architecture, midcaps is the layer that helps us control that instead of making the final classification layer control it. Yeah, so that's the use of midcaps that we have.
Thank you.
All right. Any other questions for Mudit?
Yeah, I'm up for chat if anybody wants to like talk about CapsNet or this work or anything else.
Yeah. So any other questions for Mudit? All right. So thanks again for joining us on the invited paper session on content understanding. This concludes the session for today, and have a good day. See you all. Thank you. Bye.